Hi, everybody. Welcome to this Fiveable live stream on free body diagrams for AP Physics 1. Pretty much we're going to focus on just what is a free body diagram, how do we represent forces in picture form, and then some practice problems afterwards. So let's talk about what's coming up next. There we go. So in this stream, we're doing intro to forces. We're going to go over some of the common types of forces. We're going to go over the rules for drawing free body diagrams. And then because forces are vectors, we'll go a little bit into some vector trig and some common situations that you're going to have to use trig for when you're doing free body diagram problems. And then we'll end with some practice problems with drawing free body diagrams for various situations you might run across. At any time, if you guys have questions or concerns or just want clarification, please just throw something up in the chat and I will do my best to answer it as quickly as possible. So let's start off with what are forces? So when I say the word force, in a physics sense, we're talking about one of two things. At the most basic level, a force is either, let's see, click. There you go. It's either a push or a pull. And that is the simplest definition of a force. And that's the same, you've probably heard that since, I'm going to guess, elementary school, that if you're putting a force on something, you are pushing on something or you're pulling on something. And we can think of forces as this giant tug of war to see which side wins and what's that object going to do because of that. The unit for all our forces is the Newton. Newton, named after Sir Isaac Newton, who discovered, quote unquote, the force of gravity by having an apple fall on his head. He gets credit for describing a lot of these forces and the rules behind them. And in his honor, we named the unit, or the SI unit for forces, after it. If you're American, we also talk about forces in terms of pounds, but that is in our common everyday language. We'll talk about my weight is so many pounds or this weighs so many pounds. That's talking about forces, and that is our American unit for it. Metric, we're going to talk about newtons, and because we're in science, metric is where we're going to stick with. So there are basically four types of forces, fundamentally, at the most basic level. And forces can be caused by contact with something. So if I physically push on an object, I have to push my car out of a ditch, or I kick a soccer ball, or I climb up a rope, I'm physically putting contact on them. And that is one way we could talk about a force. It could be an applied force, like me pushing on something, tension because of a rope or in a rubber band or a spring, or friction when you're walking across the ground. The contact with your feet and the ground causes that force to be there. Or it can be caused by a field and doesn't need any sort of contact at all. That field most commonly is gravitational. I don't have to be touching the earth in order to be pulled down towards it. A ball that's thrown up in the air isn't touching the earth, but gravity still acts on it, accelerates it downwards because of that force. Other common ones that are field forces are electrostatics. So charged objects, positives and negatives, likes repel, opposites attract. And magnetic, North Pole, South Pole attracts, and then North, North, South, South, they repel each other. Those don't have to be in contact for that force to occur. It just has to be in proximity to it. Okay. So we can have contact forces, physical touch needed there, and then field forces, you don't have to be in contact, just be close to the object is enough to create that force. All right, so forces can be broken down into four fundamental forces, and these are, as far as we know right now, the four basic forces in the universe. And everything from physics, chemistry, biology, any science, anything you can think about, all can trace its origin back to these four forces. So gravity is the big one that is super common. If there hasn't been, there will be a stream pretty soon, maybe next week, about the nature of gravity and deriving this Fg equals gm1 m2 over r squared equation and how that works with figuring out weight and how does that change when you're on different planets and stuff like that. Super common force, definitely one of the big ones we will be dealing with when we do forces and free body diagrams. The second fundamental force is electromagnetism. It's very similar to gravity in that the math is very similar behind it. Same sort of relationship, same sort of graph patterns between how strong it is and the distance. We'll typically cover this one when we do electrostatics, which is later in the year. I'm going to guess sometime around February, March timeframe, when we start getting into electricity and stuff like that. But that is another force that will show up, and because it's a force, it could show up on a free body diagram as well. The last two, the strong nuclear force and the weak nuclear force, will show up in AP Physics 2, and or if you're doing AP Chem or other classes like that. We're not going to get into those two, but they are forces, and they play a big role in holding. Strong nuclear force holds the nucleus together, and the weak force is responsible for something about radioactive decay. And the weak force is kind of complicated, and that's typically what my students would need to know is it's responsible for half-lives and nuclear decay and stuff like that. So for forces, we're going to really focus on gravity in the short term. Electromagnetism comes up in the long term, and then strong and weak ones come up either next year or in your future science career. They could show up in there. But those are our forces that are super fundamental, the most basic forces in the universe. All right. Questions so far? Or I should ask, is this all familiar stuff to you guys, or am I repeating stuff you've already heard? Okay, so seems like this is pretty familiar, or at least the gravity, electrostatics, different forces, sort of stuff like that has been heard before. So let's talk about how we represent forces. So a free body diagram's job is to take these abstract things like gravity and friction and tension and help us visualize what's going on with them. So to do that, we're going to draw these pictures, and we're going to use these common symbols for the forces. Typically, a force will always start with the letter F, capital, because it's a force. Now, on some questions, you may see it as a lowercase f. That's fine. But personally, for me, in my classes and my experience, capital F has been the common term we have used to describe force for the foreseeable past and foreseeable future. Then we take that generic force, F, and we start putting little subscripts on it. So F with a little g is the force of gravity. Again, if you're using an older textbook or your teacher has older question sets, they may use W for that, for weight. I don't like that so much because W is also the symbol for work, and I don't want to double dip on symbols in there. So for me, I like FG, or later on, once we've covered gravity some more on a different stream, we can use mg, because mass times the acceleration due to gravity is how you calculate your weight when you're on Earth. So that one also shows up very commonly and actually helps a lot with the mathematics behind it too. Okay. We have FF, capital F, lowercase f, the force of friction. This again, you may get with different symbols depending on the question, but this is the fairly standard one for that. We've got F sub T, force of tension. Commonly, this one also gets a capital T. Capital T has other meanings as well, but they're pretty clear as to what we're talking about. So I may fall into the habit of using capital T as well, but FT is perfectly fine and perfectly usable as well. Okay. FE, that electrostatic force, that force that we talked about coming up in the future, is going to be pretty much the symbol for it. It might be a lowercase e in there, but that is fairly standard for that. Okay. So we have a long list of forces. Now let's talk about how we go about drawing these free body diagrams. So there's really only a couple rules. Rule number one, we draw our forces as arrows. Now, why do we draw our forces as arrows? Anybody got an idea? Why would you draw a force as an arrow and not just a straight line? All right, if you got an idea, throw it up in the chat. if you're comfortable with that. All right, so we draw forces as arrows because forces are a vector. And any vector we want to represent on a picture could be a velocity, could be an acceleration, displacement, anything like that. We're always going to draw them as an arrow. So free body diagram rule number 1, we draw our forces as arrows. And rule number 2, we draw them from the center of our object. So typically, we're going to represent our object as a dot or a box or a circle, and then we draw our arrows acting from the center of that. Every once in a while, you'll get a question that wants to be super specific, and they'll say, draw them from the point of contact, where they originate from, which would mean like friction originates from where the object touches the ground. Gravity originates from the center. But for these, most of the time, it's not going to matter. Draw them from the center of the object unless the question specifically states that there is another reason for not doing it like that. All right. And those are our 2 questions. Those are our 2 rules for free body diagrams. Draw them as arrows, draw them from the center of the object. Okay. And now, just like any other vector quantity, your arrows point in the direction the force points, and their length determines the size of that force. So if it's a big force, make it a big arrow. If it's a small force, make it a small arrow, and try to get them to look like the right sizes on there. The AP exam isn't going to expect you, like some other exams might, to get a ruler and do everything perfectly to scale, but they do want to make sure that you are reasonably close with that. So if 2 objects have the same weight, their weight vectors or their force of gravity arrows should be the same length. If they have the same force of friction on them, they should be the same length, that sort of thing like that. All right. So that being said, anybody have any questions or comments about the rules so far? Are we ready to move on? Okay, so let's take a look at our first free body diagram. So in this case, we're going to look at a box. And that box is perfectly stationary, sitting on a nice, flat, horizontal table. All right, so this box sitting right on the table, how many forces do you think are on the box? Is there just one force acting on the box? Are there 2 forces? 3, 4, 5? Throw up a number in the chat, and then we'll walk through putting them on there and seeing where they're going to go. So George says 2, question mark. Is that super confident, or I'm not sure on there? Well, let's go through. So George says 2. If there were 2 forces on the box, what could they be? All right. Yeah, so George says gravitational and normal force. I always have my kids start off with gravitational because that is always acting on an object. So the first force, gravity, gravitational, pulls straight down. And again, depending on what you're comfortable with, you could label this as FG or M1G if you're talking about the mass of the object times the acceleration due to gravity. You could make it a W if that's what your question or textbook's referring to. All that stuff works perfectly fine for this. But gravity always goes directly towards the center of the Earth, which in our case is straight down. It doesn't matter what you put your object on, gravity is always pointing straight down. And the second one is the normal force. The normal force is by definition perpendicular to the surface. So our surface here is that flat horizontal table, and the normal force points straight upwards. So we have gravity going down, normal force going straight up, and it must be equal to the force of gravity when it's on a flat surface. And the reason for that is this box is not accelerating upwards or sinking down into the table. It doesn't have any acceleration. It's stationary, which means those two forces are equal. Okay? If you guys have done a Newton's first law, Newton's second law sort of lesson already, we'll just address it right now. If these forces are equal, the object's motion does not change. So a box sitting on the table stays sitting on the table. If they are unequal, the box's motion does change. It accelerates, and you'll see this jump up or jump down. All right. So this is the most basic free body diagram we can really get to is you have an object sitting on a table. It's not moving. It's not accelerating. You've got two forces, an up and a down. Right? Now, let's do the same thing, but this time it'll be a box that I'm going to push on. So I'm going to take this box and start pushing on it, trying to get it to move, but it's not moving yet. Okay? How does that change the number of forces? Sorry, George. I am by definition, and I guess this is always up for interpretation, I'm going to push it to the right. So I will have an arrow pushing it to the right, and then it's not going to move at all. I should have been more clear about that. I'm sorry. So with this box sitting right there, getting pushed to the right, yeah, now we don't have two forces anymore. We have four of them. So we've got our applied force. This is the person pushing on the box, physically yanking on it or pulling on it with a rope. That part doesn't really matter, but somebody's pushing it to the right. The box still has weight. It still has gravity pulling down on it. The fact that I'm now pushing it sideways does not change the fact that gravity still pulls down on it, that we still have a weight and stuff like that. We still have our normal force. And that normal force is still equal to the downward force of gravity. Up and down are still equal to each other because that box is not accelerating up or down. But what we do have now is a force going to the left, and that is the force of friction. Friction is what's holding this box in place, and I know that it's holding the box in place because we're told it's stationary. That also means that the backwards purple arrow force of friction must be equal to the applied force going to the right. So in this case, because we're stationary, up and down are equal, and left and right have to be equal. All our forces, both in the x direction and y direction, must cancel each other out. Okay? If they didn't, our box would no longer be stationary, and then it would start accelerating in a given direction. Okay? And as far as friction goes, I know in a later stream, we're going to be delving into the different types of friction. How do we calculate that, what that's determined on, and stuff like that. So stay tuned for that stream coming up at a future date. That might be next week on there. So because we're stationary, up and down equal, left and right equal. And again, if I wasn't pushing on it, that friction disappears and we're just left with an up and a down. All right. So right now, I think, yeah, we're going to just take a quick check in here. Scale of 1 to 5, 5 being I got this, this is simple, move on. 1 meaning I have no idea what you just said. How comfortable are we feeling with this basic up, down, left, right forces free body diagram stuff? Okay, Grace is 5, excellent. So I guess I should ask you guys, have you guys done a physics class before? I mean, is this all old stuff or is this brand new and I'm just doing a great job? Just so I don't have to cover stuff we already know about. Okay. So let's jump to the next one then. So up, down, left, right, pretty good. Brand new, covered in class yesterday. Okay, great. So hopefully this is a good refresher. So let's go a little bit ahead now. I'm going to take that same box and I'm going to now pull on it, not just sideways like in the previous example, but now at some angle theta. And this is where, again, things get a little bit more complicated. And this is where we have to start talking about, we have an angle, there's some trig involved here. Okay, so for this type of question, and this is most of the AP1 questions are going to be of this general type, involving some sort of angle, and you have to do some trig to figure stuff out. All right, so let's go through the forces that are acting on this box. Stationary box sitting on the ground, pulled on by a rope, but that rope is now at some sort of angle. Right, so our first super basic force always has to be there is gravity. Goes straight down, nothing super different about that. So in all of our examples so far, whether I'm just letting it sit there, pulling on or pushing on it sideways, or now pulling on it at an angle, gravity is still there, still pulling straight down, doing its thing. We also have a normal force pushing up, and that's the ground pushing up on our box. We've got this force from the rope. This could be a T or an FT, depending on what you want to do. It's also perfectly fine if you call this an applied force instead of a tension. It's all equally valid in the eyes of the exam. Okay. And finally, we've got friction going backwards. I need to have a force going backwards, otherwise this box would be pulled to the right. But something's different here. If you guys look at the size of the normal force, what's different about that compared to our previous examples? All right, so how is, let's see if I can find my laser pointer. How is this normal force in this example different from the normal force in this example? And specifically focusing in on the size of that normal force. Yes, exactly. It's smaller than the force of gravity. They're not equal. And the reason for this is when you're just having it sit on a table or sit on the floor, up and down are equal because there's nothing else pushing up on it. But the problem here is that this rope, this tension right here, is pulling both sideways and vertically. It has both components going on here. So what that means for us, and again, if you guys have done Newton's laws, this is another thing that's coming up here, that the normal force, this upward green arrow, plus however much upward force this tension is pulling, which is T sine theta because we're opposite of this angle, those two vertical forces must be equal to the downward force of gravity. And that means that our normal force is less than the force of gravity because we have this other upward force going on. This also means that our force of friction is not equal to the tension in the rope, but it's equal to the horizontal part of this tension. Okay? So because we have this rope at an angle now, we can't just treat that as a single force going X or Y. We have to use trig to break it down. Just like you would have had to do if this was a projectile motion question and a ball was kicked at an angle, you had to find V naught X and V naught Y. The same basic idea applies here. Any force we have at an angle, we can break down and turn it into just a horizontal part of it and just a vertical part of it. And that skill is going to be super, super important when we look at, in a later stream, static equilibrium and stuff like that, and try to figure out what's the tension in one of these ropes or one of these forces, what's the value of stuff like that with it when we have things at angles and such. All right, so does that make sense? And there we have to do some trig because that rope is not pointing either horizontally or vertically, it's doing both. And then all the upward forces have to cancel each other out, and all the sideways forces, all the horizontal forces need to cancel each other out. Okay. So this one, again, fairly common that we're going to see questions like this. And I'm not getting super far into the math right now, except for saying that, hey, this is what we need to do with it. That comes in a later stream. Probably actually, that may be today, later than this. I'm not sure. But it's definitely coming up with, I think Chris is doing it. Okay. The next most common free body diagram you'll have to draw. So we've kind of done the sitting on a table, up, down, left, right sort of things. We've done the sitting on a surface at with an angle pull. This is the third most common free body diagram one that we're going to have to do. And this is a box sitting on a ramp, and that ramp has friction. Okay, so this box is perfectly stationary on this ramp. This ramp is at some angle theta above the horizontal. Normally it's a 30-degree angle just based on previous AP questions, but it could be any angle. It doesn't really matter. So let's go through our forces for this one. What's one force that is acting on this box? Gravity. And which way should gravity point on our free body diagram? Straight down, exactly. So we have the force of gravity going straight down towards the center of the earth. Okay, and that's true, again, for any situation we are talking about with a free body diagram, gravity is going to point straight down towards the earth. Okay, what's another force that has to be there? Normal force. Good. Normal force, by definition, has to point which way? Perpendicular. Thank you, Reagan. Perpendicular to the surface. So I have this normal force going up perpendicular. Now, notice these two aren't pointing the same direction anymore. Up until this point, they've always been gravity down, normal force up. But now, no. Normal force perpendicular to our surface, gravity straight down. We're not going to go the same direction. They're not going to cancel each other out anymore. All right, another force that's acting on our object. And friction. Okay, now this one might be a bit tricky. Which way should friction point in this diagram? To the right, yes. Yeah, to the right. I know what you're trying to say. I would say up the ramp or up the parallel to the surface, because it's not going to be a straight going to the right. It's going to be up that incline in there. But that's that force of friction in there. So we have those three forces acting on our object to hold it in place. Now, have you guys done the trig for a box on a ramp yet, or is that something new? Not yet. Okay. So in this case, we know those three forces have to cancel each other out. That somehow this box has to be stationary, so all the forces on it add up to be zero. But none of them point the same directions. It's not as simple as saying back when we were doing the box sitting on a table, up and down cancel out because they're going opposite directions, and left and right cancel out. Here, there is no up and down. I've got down, I've got perpendicular, and I've got parallel to the surface. So what we need to do is we need to pick one of these three forces and turn it into its components. Find the part of it that is horizontal and vertical, or perpendicular and parallel. And the one that we do this with is the weight vector. So the weight vector pointing straight down. We're going to break this up into two parts. We're going to break it up into a right triangle, and by the magic of geometry, this angle in the upper part of this triangle is the same angle as the ramp, and it's wonderful that that is. So we can break this up as some part of gravity is going straight down, sorry, not straight down, perpendicularly into the ramp, and this blue dashed arrow is going to be canceling out my normal force. The part here, playing connect the dots, parallel to the ramp, well, this one has to be how much my force of friction is. And again, we can use trig to figure out those values. So this perpendicular side is adjacent to my angle, so I'm going to use cosine to find that. And the opposite side, this parallel part, gets the sine term. So it's the hypotenuse times the sine of theta for the opposite, and the hypotenuse times the adjacent side times the cos of the angle for the adjacent side. And if we put all that together, it means that the normal force perpendicular away must be equal to the perpendicular part of gravity, Fg cos theta, and the force of friction going up the ramp must be equal to the parallel part going down the ramp, Fg sine theta. Okay? And when I tell my students that these are super important, I make them memorize it, simply because these come up so often in many situations, with friction, without friction, with normal force and stuff like that, that knowing these right off the top of your head is super handy in there. This also opens the door for a lot of math later on when we delve into how do you calculate force of friction on a ramp and stuff like that. And it's a pretty cool lab that you may do in your classroom. And it's a lab that has shown up on the AP as one of the constructed responses, which is how can you figure out the coefficient of friction on a ramp using only a protractor. And we'll table that for a second and get back to that when we do friction, but that'll definitely be one that shows up on there as well. All right. So going back to box on a ramp, this is our third super common, free body diagram. That's the right word. On here, you've got gravity straight down, normal first perpendicular, force of friction up the ramp, and then we break up the weight of the box into its components, and that lets us calculate, if we needed to, the normal force and the force of friction. All right, so that was free body diagrams in a nutshell. Same questions before. Out of 5, I got this. 1, please say that all over again. I don't know what I really confused what we're saying. How are we doing here? Okay, thank you, Reagan. Okay, cool. And Grace, is it just the new trig part that was confusing? Okay. So good news is I'm kind of done with the trig for right now. Pretty much what I had planned left was just to do some practice problems with this. Now, if you guys, I'm not sure if you're on mobile or not, but at the bottom of your screen, there should be a little blue box that says practice worksheet. If you guys can click that and open that up, that's the one I'm going to be working off of next, I think. Yep. Okay. Or we can just kind of do it here and just talk our way through it. But I am going to switch my screen for a second so I can draw out some answers. So give me a second to switch over to that, and then we will go from there. All right. I need to stop sharing, close video. Good. And then I need to do this one, and then this one, and then this one. Let's see if this works. Okay. So again, and hopefully this camera is going to be bright enough to work with here. This is a worksheet that I give to my EP kids to basically just let them practice more and more of how to draw free body diagrams, because this is one skill that when we pretty much once you learn forces, every single force question you look at will have a free body diagram with it, either asked in the question or one that you just draw yourself, because it makes it a whole lot easier to understand what's going on. So we're going to go through a few of these. If these get too simple and you guys want something more challenging, please just let me know. So number one, a book is at rest on a tabletop. Draw the forces acting on the book. Okay, so I'm going to ask these questions a lot, apparently. How many forces are acting on the book? Reagan says 2. So there are 2 forces. There we go. Grace did 2. Okay, so 2 forces acting on the book. We've got gravity going straight down and our normal force going straight up. And is there anything else we can say about the length of those 2 forces? They must be equal. Good. And I know they must be equal because that book is at rest and it's not accelerating any direction at all. Okay. Let's jump ahead. I'm going to jump up to number 3 because why not? Move my camera out of the way here. Good job, camera. All right. So this one, we have an egg or a ball or something like that falling through the air. We get to ignore air resistance, which is nice. How many forces are acting on this object? One. Yes, there is only one force acting on it, and that is our force of gravity. Okay. Number 4, same question. This time we can't ignore air resistance. What do we know about the forces now? How many are we talking about here? Okay, Grace says 2. All right, so I know there's gravity. That's got to go down. What's the other force I need to put in here? Okay, so air resistance, which way should that point? Up, yes. Okay, so I don't have a good symbol for air resistance, so I'm just going to call it F air. Depending on the question, that might be an FF as a friction. That might just be FA, but F air is also what I'm going to use for it. Now, is there anything we can say about the size of those 2 vectors based on this question? Okay, so Grace, you're saying gravity is greater, and that's definitely a possibility. It may also be equal. They don't actually tell us enough information in this question to actually make that call. I'm going to leave them here and not make any sort of claim whatsoever, which one's bigger or smaller, but they may be equal. If this actually reached terminal velocity and is falling at the fastest speed it could be, those up and down forces would be equal. But there's nothing in this question that says we've reached that, and there's nothing that says we haven't either. So I'm going to leave it just like this. They're unequal. Air is bigger, but also just know that they may have been equal, and we just didn't know about it. Okay. All right. So next one, number 5. A rightward force is applied to a book in order to move it across a desk with a rightward acceleration. We have friction. We get to ignore air resistance, diagram the forces. Okay, so how many forces on this book? We got 4. Good. So we have down, gravity, up, normal, We are pushing this thing to the right, so I'm going to just call that an FA, and that means friction has to point backwards to the left. Okay, any claims we can make here about the size of the forces, or which one's bigger or smaller or equal to each other? Right, so Grace says up and down must be equal, and that is absolutely correct. And I know that up and down have to be equal because we aren't accelerating up or down. Okay, now there's one more claim we can make about this, because we know we are accelerating to the right. This means that, yes, the applied force needs to be bigger than the force of friction. So really, had I drawn this right, let me get a different color here, this one should be significantly shorter than the acceleration or the applied force. So I shouldn't have done that. I should have had it just be short like that. Okay. Now I need to plug my phone in here so this camera doesn't die. So let's do a little moving here for a second and plug in and charge, maybe. Hey, that's better. Okay. So we're just going to shift a little bit here. Okay. There we go. Number 6. The same book. We're pushing out at the same. How is number 6 different from number 5? All right, so what's different in number 6 compared to number 5? Yes, both of you. Good job, Reagan. Good job, Grace. This is constant velocity. Those two words are the most important part of this question because it means that all our forces must be equal. So we still have the same 4 forces, left, right, up, and down. Applied, gravity, normal, and friction. Friction and applied must be equal. Normal and gravity must be equal. Everything is constant or cancels each other out, perfectly constant. All right. I'm going to skip ahead then because it seems like you guys got these basic ones down pretty good. So I'm going to jump ahead a bit on my little cheat sheet here. Let's look at number 11. A car is coasting to the right and slowing down. Diagram the forces acting on the car. All right. You're driving a car or in a car, coasting to the right, and you are slowing down. How many forces act on this car? Reagan, yes, there would be friction. We also know that there's friction going on here because if there wasn't friction, the car wouldn't slow down. So we know there is friction going on because that's what's going to bring this car to a stop. Just this way. Yeah, now I can write better. So there must be friction here because we are slowing down. Which way would that friction point? To the left or to the right? Or up or down, I guess. Yeah, it's got to go to the left. Friction always goes opposite the direction we are moving. So in this case, the car is going to the right. Friction must point to the left. And then again, we also have a car, so which means we have our gravity and our normal force hanging up for fun. And just like in all our other examples on a constant surface, they are equal to each other. All right. Any other questions right now before we move on to some more practice stuff? How about 1 through 5? How are we feeling about these? Okay, Grace says good. All right, so we've got a few minutes left before we're going to call this good. Let's just do a few more ones that are, I'll say, a little bit more uncommon here. So let's look at number 7. Number 7 says we have an object suspended from a ceiling by, I'm guessing, 2 ropes or 2 cables or 2 something like that. What would a free body diagram for this thing look like? And I'm going to draw off to the side here because I got space. So there's my object. How many forces act on this object? And there are 3 of them. Yes. We've got gravity going down. And then they're ropes, I'm going to guess. So I'm going to call them tensions. And this is where you get to decide what we call each of these. I'm going to call one T1 and the other one T2 for tension rope 1, tension rope 2. But you can flip-flop those around or change it however else you want to. That's really up to you as far as which ones you choose for that. Okay. So as long as you're clear in your free body diagram, what you're labeling things, the labels you choose are fairly open to your interpretation. The only exceptions to that are when the question specifically says, define them as T1, T2, FA, FB, that sort of stuff like that. But in general, you guys have the freedom to choose what labels you put on things. Okay. All right, number 8. Let's take a look at that one. So I guess this object is motionless. So I'm going to start with, there must be gravity pulling down on it because gravity pulls down on everything. Then I've got 2 tensions. One going to the right, I'll call that one T1, and one going off this way that I will call T2. Again, if you flip-flop your T1 and T2 or call it TA and TB, TH and T not H, the options are up to you as far as that goes. Okay. But let's talk a little bit about this one because I'm interested to see what you guys are thinking about here. Which force is the biggest force out of all 3 of those things? Is it T1? Or sorry, with my labeling, T1, T2, or the force of gravity. Which of those 3 forces is the biggest? And again, this might depend on how much forces stuff you guys have covered already. but this is definitely a question that could show up in future stuff, and is a very common AP sort of question. Okay. Reagan says gravity. And all right, so why I should gravity, because it's pulling down, gravity because it's doing something else. Help me out here. Or is that just a guess, Reagan? I'm trying to get what's your thought process behind that, because that's typically how the AP would phrase that is, which force is bigger, explain in a well-reasoned paragraph, blah, 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 sort of stuff. Right. 9.8 G, or a surface pulling down. True, yes, absolutely. This is 9.8 times 9.81 times the mass, going straight down here. But that is not the biggest force out of all three of these. Okay. And again, if you haven't done this sort of problem before, it's a little difficult to see at first glance, but let's talk about why this is not the biggest one down. First thing is, I know this is motionless, which means I know that the up and down forces must cancel each other out, and the left and right forces must cancel each other out. Okay. The force of gravity only pulls down. This is only a vertical force. T1 is only a horizontal force. But T2 pulls at an angle. It pulls vertically enough to cancel out the force of gravity, and it pulls horizontally enough to cancel out the horizontal force. All right, so you have a right triangle here where one leg is equal to the weight of the object, the other leg is equal to the horizontal force, and in a right triangle, the hypotenuse always has to be the longest side. So if you were to think about, let's say the force of gravity is 10 newtons on this, that means this side is 10, the hypotenuse has to be bigger than 10. So the biggest force in this scenario is T2, because it's doing two jobs. It's balancing out gravity, and it's balancing out that horizontal tension. And that's why T2 has to be the biggest force in this case. I couldn't make a claim with number 7. I don't know which one's bigger. Probably the force of gravity, but I'm not positive for this one. But for this one, we can be pretty confident that T2 has to be bigger than the downwards and the right one, simply because this is canceling out both of those two forces. So it must be bigger. Does that make sense? Okay, good. Okay, so I guess at this point, I am pretty much out of practice problems. Unless we want to do, I got 2 more here that we could do. But really, do you guys have any other questions, any concerns, anything I can spend the last couple minutes going over or readdressing for you guys? All right. Well, I guess the chat's quiet, so I'm guessing no questions right now, and that's fine. So I'll just go ahead and do the last 2 questions here, and then we'll end the stream, and we'll go from there. So number 9, object's motionless. I don't know if there's friction or not. I actually have no idea about this, but I'm going to assume that what we've got is a tension going up the ramp, a normal force going perpendicular, gravity going straight down, and then those three just kind of cancel everything out, because if there was a friction, it'd probably go up the ramp again, but I don't know for sure if it's there or not, and this doesn't specify enough that it's frictionless. So maybe there's 4, maybe there's 3. I don't know for sure. We'll call it something like that. And then number 10, the object is motionless. So we've got our object. We've got a normal force from the vertical ramp. I'll call it Fn1. We've got a perpendicular part here. That's Fn2. Normal force 1. That one, normal force 2. This one. And then finally, gravity pulling straight down. And those are the last two. Realistically, when I teach forces to my students, I focus a lot on questions like this one, and these where you have multiple things going at angles and stuff like that. It also comes up fairly frequently that we are doing simpler stuff like you're at a constant speed, you're moving and stuff like that on there. But I would say if you guys understand how to draw these two, you're in great shape for future forces and stuff like that going on there. All right. And with that, unless you guys have any questions, I'll just say thank you for a great stream, and I will be back here next Wednesday. I think I'm doing friction next week, but we'll see. We'll see what I'm doing. But physics stream again Wednesday, and I think there's another one starting in about an hour on nature of forces and stuff like that as well. So you're welcome, and thank you guys. Have a great night.